Okay, so where we left off was we had our function. It went from a to b, and I'll just set you up again. We subdivided this up into an equal number of pieces, so n subintervals. You remember that subintervals were created by the partition of that interval into points, where we just said let x0 be the left endpoint, let xn be the right endpoint, and then delta x for a regular partition would just be the width of the entire interval divided by the number of pieces. And then we said what? We could form the Riemann sum. Remember what a Riemann sum was? It's just our sum of rectangles, where each rectangle area is a function value at a selected point from inside that subinterval times the delta x. So just remember, when I say ck and the summation's going from 1 to n, I mean this is f of c1 plus f of c2 all the way up through f of cn all times delta x. And these c numbers are being picked randomly from inside each subinterval. Okay, I think where we left off last week is we had talked about the upper sum and the lower sum, and there's a little bit of advanced calculus that we didn't pull into the conversation, but we at least justified the idea, I think, that u minus L had to be approaching 0 as n approaches infinity in a regular partition. And I think from there we figured out that the limit as n goes to infinity of the upper sum and the limit as n goes to infinity of the lower sum would both be equal to each other if they exist. And then the true area under the curve is where? It's in between these. And so we said if you took the limit of each of these and you got an answer, so let's say you took the limit of the upper sum and you got an answer, and you took the limit of the upper sum and you got the same answer because these two are equal, then if those two exist, what's the true area in the middle? Same thing because of the sandwich theorem. So far so good? Is that about where we left off? Okay. Now, again, there's one little thing I'm going to wave my hand on here. We could prove it, but it's kind of intricate. The one thing we've left unsettled here is how do I know that these two actually exist? What we demonstrated last week was if these two exist, they are equal. And if they're equal, the true area will be that same limit. The question is, how do I know these two actually exist? And there's a theorem for that, which I'm just going to quote now. If f of x is continuous on the closed interval a to b, then the limit of the Riemann sum exists for any partition scheme. And really what's hidden behind that is I'm implying that the upper sum and the lower sum exist, and this limit of the Riemann sum is in between them and it exists. In other words, what is the only sufficient condition you need to make sure we can actually do this limit idea that we're talking about? The function need only be continuous on that interval. That's all it takes. Alright, now, when this limit exists, we say f of x is integrable on the closed interval, and we write integral symbol, so like our antiderivative symbol, except now at the bottom and the top of the integral symbol we put an a and a b. A the left limit, b the right limit of the function dx. So in other words, it looks just like our antiderivative symbol, except I'm putting the left and right endpoints of the interval right there and right there. We'll write that that is equal to the limit as n goes to infinity, summation k equals 1 to n f of ck delta x. So just to reiterate here, if this guy exists, which it will if the function is continuous, we're now going to write that as integral from a to b f of x dx. And we're going to call this thing that I just wrote the definite integral. Okay, so Ethan just asked, jumps and holes mean not integrable on that interval. Okay, so I'll answer that question next. And you can think about this in terms of area. So this guy is continuous, and it should seem intuitive to you all by now that because it's continuous, I should be able to subdivide the interval however I want, create subintervals, create rectangles, add them up, and because of the connectedness of the curve, the more I do this, doesn't seem like I'd run into any problems. What if the function had a discontinuity? In fact, let's say it's one like this. Let's say this is A, let's say this is B. And so if I say let's calculate the limit of the Riemann sum of that function over that interval, would the area under that curve still exist? So forget about the limit stuff for a minute. Is there actually a finite area under that curve? Yeah. Looks like I should just be able to, if I sort of think about splitting it right there, there's definitely an area here, and then there's definitely another area, sort of, that's not the color I wanted, and then there's sort of another area here. Everybody with me there? So if this number was C right here, could I say that the area under that curve is the integral of the function from A to C plus the integral from C to B? And if this is our new designation, this so-called definite integral for the limit of the Riemann sum, this should give me the yellow area in the picture. This should give me the orange. Okay, which means the answer to your question is, for this picture, the function is still integrable on this interval. Okay, now why? For one thing, well, the most important thing is this discontinuity. Well, it's not removable, but it is finite. Yeah, so Ethan says, does endpoint inclusion matter here? Okay, so since that's just a point, which is dimensionless, and you're calculating area under the curve, that A is like an instantaneous stopping point, and that goes for the C also. So inclusion or exclusion of the endpoints or the division point in the middle doesn't really affect the area. Now does everybody see what I'm saying here? The reason this worked, the reason I could find an area under that curve, is because this jump right here was finite. If that had been a vertical asymptote where that graph went up forever, we wouldn't be talking about a finite area under the curve. Okay, so the real answer to your question, Ethan, which the Calc 1 books never state it this way, we could modify our theorem and say if f of x is continuous except possibly at a finite number of finite discontinuities, f of x will be integrable. Actually, you can make it even a stronger statement. You can say that f of x is continuous except possibly at a countably infinite number of finite discontinuities. F of x will still be integrable, but we don't ever talk about that in Calc 1. But it's okay to talk about finite number of finite discontinuities. And of course, you'll be able to do this because what's the only thing I had to do to deal with this problem? I located the discontinuity and then I split it into two separate definite integrals. One for the area to the left of the discontinuity, one for the area to the right. And so if I have some sort of curve where there is a finite discontinuity, just break it into different integrals and add them up. Because if this is to be interpreted as area, so let's see, with a normal curve with just a hole, can we integrate like normal? Okay, so question is, if we had something like this, let's say from A to B, and so this is f of x, where f of x is defined everywhere except at C. Is it okay to integrate just from A to B f of x dx? Technically, no. Technically, you really do need to go from A to C and then C to B. And I'll tell you what, we'll save that one for when we get to, you'll see when we get there. Technically, we do need to do this, but in a cheaty way, we will be able to just do it from A to B. So you're asking the right question. What happens if it's not a jump and it's just a hole? Won't be a problem when we get there. Now, of course, again, what is a problem is if I have some sort of, if I have an asymptote, then what we're talking about here is out of the question. Now, not necessarily out of the question when we get to Calc 2. Sometimes integrals like this exist. That is, sometimes there is a limit to the amount of area under that curve, even though there's a vertical asymptote there. Sometimes there's not. But that's another story. Alright, so now we're ready to proceed here. Now we know if this limit exists. We're going to call it by this name, the definite integral from A to B of f of x with respect to x. Note, make sure you understand the difference between this and this. This one is an antiderivative, or let's say family of antiderivatives, because you know your answer should have a plus c in it. Okay, at this point, is everybody clear that this does not mean antiderivative right now? Right now, the definition for this that I just wrote is this limit up here. So right now, even though we're using this integral symbol, right now this has no meaning in terms of antiderivatives. We don't know anything like that yet. Although, from our example earlier with finding the area under the velocity curve, we are guessing that this has something to do with the antiderivative of this function evaluated at these two numbers. So in particular, when it was the velocity function that we were finding the area under and we went from A to B, didn't we say that that was the position at time B minus the position at time A? So if I said the derivative of big F is little f, that's just another way of saying what? Big F is an antiderivative of little f. With me there? Can you all extrapolate here from this example what we're guessing? If I took the integral from a to b of f of x dx, what does it look like happen in our velocity example? We took the antiderivative of velocity, which was position. In this case, we're saying what? When you take the antiderivative of little f, you get big F. And if something like this is going to be true, this looks like down here it would be the antiderivative of little f evaluated at b minus that same antiderivative evaluated at a. And this would be the general version of what it looks like happened in our velocity example. Okay, this statement is true, but we don't know this yet. You can't use it yet. What you're going to have to do at this point is calculate this from the limit. And so I'll do a couple of those for you now. We've got time to get at least 2 done, I think. And then if we need to, we'll do another couple tomorrow. Okay, just to reiterate one more thing here. Make sure you understand this one is called the indefinite integral. If you look back in your notes, that's what we called it back then. That's the one that's just asking you for the antiderivative. This new one, where I'm putting these limits in, and now this is interpreted as the limit of a Riemann sum. This is the one we're calling the definite integral. Obviously, what I'm hinting at here very strongly is there's a big connection between these. But right now, if I ask you to compute something like, let's say, integral from 1 to 3 x squared dx, what is your interpretation of that right now? Well, it should be the x squared graph from x equals 1 to x equals 3. And if that's a positive function, I would definitely interpret that as the area under the curve. Everybody with me so far? Alright, now, if that's 1 and that's 3, what's the first step to building your Riemann sum? Do the partition. Partition into n equal subintervals. If you do that, what's delta x for each one of those n subintervals? Okay, everybody agree with Andrew? We did say it would be the overall width of the interval divided by the number of pieces. That looks right to me. Okay, what's next? Well, you form the Riemann sum, which is the sum of n rectangles, each one of which is a height, which you're getting by calculating the function at some number in the interval, times the width of the subinterval, which is uniformly 2 over n for every one of them. So the question is, really, how do we pick the CKs? Okay, Okay, so question for you. From what we talked about last time, does it matter where I pick the CKs? Does it matter if I pick the left endpoint, the right endpoint, the midpoint, or any other arbitrary point from each subinterval? Will it matter once I take the limit? No, absolutely not. So, you pick something easy. Alright, what's the simplest thing? Well, think about what we've been doing all along. If this is x0, and this is x1, and this is x2, and so on, seems like the easiest thing would be to pick the left endpoint or the right endpoint. And again, we've seen examples where the midpoint gives you a better approximation, but since we're going to end up taking a limit on this thing, I don't really care what points I pick. So let's say I wanted to pick the right endpoint of each subinterval. So that means I would be picking this guy, this guy, this guy, and so on. With me so far? So in other words, we're saying C1 would be x1, C2 would be x2, and so on. With me? Alright, now question. In our situation, what's the x0 here? It's 1, isn't it? What's this value right here? Can somebody tell me what that is? We started at 1. We divide the interval into n parts. Each one of these is how wide? Okay, so Andrew says 1 plus 2 over n, which is correct. How are you getting from the left endpoint of that first interval to the right endpoint? You are adding the width. What's this guy? Do it again. Does that look right? With me there? We're adding 2 over n to get from here to here. We're adding 2 over n to get from here to here, that is to the right endpoint of the second subinterval. How am I going to get to here? I'm going to do it again, which means this would be 1 plus 3 times 2 over n. With me so far? Or let's ask it this way. Anybody not sure where I'm coming up with those? Let's say I've gone out to, so you know, this is the first subinterval. This is the second one. This is the third one. Let's say I've gone out here to the kth one. Let's say this is the kth subinterval, which means this is xk and this is xk minus 1. Okay, down here at the bottom, what are we saying the first point is? It was the first endpoint, which was 1 plus 2 over n. What's the second c that I selected? It's the right endpoint of the second subinterval, which was 1 plus 2 of those. What's the number I picked in the third subinterval? It was 1 plus 3 of those. By the time I get out to this kth one, what's that kth one going to be? What's the magic formula? Yep, Ethan says it's 1 plus k of those. Or this, as he puts it, 1 plus 2k over n. Okay, is everybody with me on that formula right there, in particular this part. Because if you really look what that's saying, isn't it saying that ck is equal to a plus k times delta x? A was the left endpoint over all of your interval. K is the count of the interval you're in, first, second, third, fourth, so on. What's this guy right here? He's the delta x. And you're just repeatedly adding delta x to get to the next endpoint, the next endpoint, and so on, until you get to the very last one. Notice, just to make sure this is right, what's Cn going to be? It's going to be 1 plus n times delta x, which is 2 over n, which gives me 1 plus 2, which gives me 3. And that puts me at the right endpoint overall. Okay, so here's what I've got. If we want right endpoints, in our, let's say, Riemann sum subintervals, we can use a formula actually. We can say that each ck is the overall left endpoint of the interval plus k times delta x. If we want left endpoints, well, can somebody tell me what ck would be there? In other words, what if I wanted that to be the first ck? So there's C1, there's C2, there's C3. Okay, so you're talking about coming from the other side. So let's see, would that work? Okay, the only problem with that, I like the thinking, if everybody's looking at the chat thing. Andrew says, would it be B, so he's saying right endpoint overall, minus k times n over 2. Okay, the only thing is, where do you want to be when k is 1? You want to be in that first subinterval. But if you're starting over here at B and you want to be back here, you're going to have to subtract, you mean n over 2, or yeah, let's make that 2 over n. So you'd have to subtract him many times to get all the way back to the beginning. And you could certainly write a formula like that. So that's good thinking. Let me push you in the direction I kind of want you to go here. What would I have to add to A to get to each one of these? If you're here and you want that point, you add nothing. Yeah. If you're here, which would be the second one, you'd have to add 2 over n once, wouldn't you? So before you were adding 2 over n once to get to the first number, twice to get to the second number, 3 times to get to the third number. Now you're going to add 2 over 1 0 times to get to the first one, 1 time to get to the second one. Closer. I'll write it down and you see if this makes sense. Would that work? So if this is A, what's C1? Well, when K is 1, this part's 0, and you're just going to get A. Important though, what's C2? Well, it's going to be A plus 2 minus 1 delta x, which is just going to be A plus delta x. So that means this is going to be your C1. The right endpoint of that first subinterval is going to be your C2. And that's also the left endpoint of the second interval. So now you're using the left endpoints. You're capturing the left endpoint of the first subinterval. You're capturing the left endpoint of the second subinterval. Now that you see it, it kind of makes sense. It's a shifting. It's just simply a shift. Now, here's the important thing. Does it matter which one of these I use? Really? No. It matters right now, but once I apply the limit to it, I know the limits are all supposed to be the same number. So the one I'm going to suggest you use the most is this one, simply because the formula is so easy. Alright, so let's do our problem. We've got time to do one thorough example, and then tomorrow we can do a few more. So our integral was 1 to 3 x squared dx. And so this should be the limit as n goes to infinity, summation k equals 1 to n, f of ck delta x. Now we've got some stuff to write out for that. Its limit as n goes to infinity, summation k equals 1 to n. Okay, what's our function here? F of x is the x squared function. And what am I plugging into it? I'm plugging in 1 plus k times 2 over n, which is 1 plus 2k over n. So if I plug that input value into that function, I think what we're talking about is 1 plus 2k over n squared. That would be this guy. Don't forget the delta x, which is easy to do. You get so happy that you've figured out this part. Sometimes it's easy to forget the delta x. So that means there should be a little times 2 over n down here at the end. Okay, now, before we go any further, any questions about this, how I'm getting that? There's two parts to this, getting the hang of this. One is constructing that limit that I just wrote down, which consists of what? Figuring out the delta x, figuring out the formula for those ck's, plugging that ck into the function, and then simply forming a summation of those, which forms the Riemann sum. Now the question is, how do I break this guy down? Well, let's write it all out. It'd be limit as n goes to infinity, summation k equals 1 to n. Let's do the algebra here. I know I can factor him out. And when I do, I'm going to get 1 plus 4k over n plus 4k squared over n squared. So far, so good. Which is limit as n goes to infinity of, let's call this sum k equals 1 to n 2 over n plus sum k equals 1 to n. Now if you notice what I'm doing here, I'm just distributing, which means when I distribute the next one, I'd have what there? 8k over n squared plus summation, looks like 8k squared over n cubed. And after we do a couple of these, you'll come up with your own ways to streamline this process a little bit. I'm just going through all the gory detail. But you can see if I distribute the delta x at the end, basically I'm breaking up this summation on the 3 terms inside, which we said we could do. Alright, question for you all. If you look at this first sum, what's the variable that's moving in this summation? Is it the k or the n? Yeah, just the k. Okay, so make sure everybody understands that. The n is a fixed number in this summation. Now, I understand out here the n is not fixed, but you're going to do that last. I'm talking about if you just look at the orange, where the summation is, it's the k that's moving from 1 to 2 to 3 to 4 up to n, which means what? As far as this summation is concerned, 2 over n is a constant. 2 over n doesn't contain k. K is the variable that's moving, so that means 2 over n is fixed as far as k is concerned, which means I can factor the 2 over n outside the sum, and of course when I do, what's left is a 1. I can do the same thing on the other sums. What part in this summation is fixed as a multiplication factor and can be factored outside the sum? What can you factor outside that summation right there? 8 over n squared. For these ones that we're doing, it is. So of course, as you'll see here in a while, there are limits to what we can handle with our little tricks here. If I start trying to do this for trig functions or log functions or square root functions, that k isn't always going to be. So what you mean is it's not a power of k or anything like that. Yeah, so if they're polynomials, the k will always be a k or a k squared or a k cubed. If we tried to adapt this to other kinds of functions, we'd have trouble. So we're basically going to try and operate on simple things where we can have whole powers of k. That's what you meant, right, Andrew? Okay, everybody with me there then? Okay, question. What's the sum k equals 1 to n of 1? Yes. Everybody agree with that? If you add up 1 n times, you get n. Plus 8 over n squared times, okay, now's when we use that thing we talked about early last week. Remember those summation formulas where I talked about math induction as the way to prove those? We basically listed 3 starting formulas, and the first one was summing up 1, 2, 3, 4, 5, 6 up through n. Anybody remember how that one went? I know James knows it. Anyone? Real close. Just change the minus. Yeah, that's right. So does everybody see what he's saying there? Change that minus to a plus, and we're saying that summation right there is actually given by this closed formula. So that means that becomes n times n plus 1 over 2. Same thing down here at the end where you have the plus 8 over n cubed times the summation of the k squareds. That was one of the other 2 formulas. Anybody remember that one? That's the one that's got the 3 parts in the top with the 6 in the bottom. Remember that? Okay, so this is why we talked about those formulas. If the terms in the function I'm trying to integrate are polynomial terms, I'm going to need these summation formulas for integral powers of k. K to the first, k squared, k cubed, and so on. Okay, with me so far? Alright, now, You don't have to go this far, but again, I'm trying to give you a real thorough example here. So I'm going to say this first part is limit n goes to infinity of 2n over n plus limit n goes to infinity 8n n plus 1 over 2n squared plus limit n goes to infinity 8n n plus 1 2n plus 1 over 6n cubed. Alright, now you should automatically be able to tell me what that one is. Yep. So we got that one. Can you tell me what this one is? Okay, everybody agree with that? That is correct. Does everybody see why? Notice he is limit n goes to infinity of 8n squared plus 8n over 2n squared. What do we know happens when we have a polynomial over another polynomial and the degrees are the same? We know the limit would be the ratio of the leading coefficients. So the limit would be 4. So really what I should be doing is eyeballing this thing and seeing that it's a second degree. And then of course the bottom's a second degree. That means this is just a rational function, which means the limit as n goes to infinity should be the ratio of the leading coefficients, which is definitely an 8:2 ratio. Definitely 4. What about this last one? If I look at the top, what's the leading term of the top if I FOILed it all out? (16n cubed). Everybody agree? And of course the bottom is just 6n cubed. Well, it doesn't matter what the other terms are in the top. If the leading power is 3 in both the top and the bottom, then again you're a rational function where the degrees are the same, which means your limit should be the ratio of those leading coefficients, which in this case would be 16 over 6, or 8/3. So I guess we've got, what, 26/3? And so what this tells us, again, is if this is the x squared graph, and we go from 1 to 3 and find the area under that curve, then this limit we just computed is the limit, or the area, under that curve and in between x equals 1 and x equals 3. That's our interpretation. What do you think? Actually, it's pretty cool. You just found an area under a curve. It will take some time, but if you notice, now that we've kind of got to there was a lot of build up to get to this, and now we did this problem like in less than 10 minutes. You can see there's nothing fancy here other than constructing the function and the sum. This part is just a bunch of algebra. It's a bunch of foiling, it's a bunch of separating summations, and then of course this part down here is where you're taking the limits. This part's not bad at all. I'd say the part that's going to bother everybody is just this algebra part, not because it's hard, but because it's tedious. Yes, we'll definitely do some more tomorrow. I'm going to put up homework for this. I'll just put it up on Blackboard because I want you to do a little bit from the book, and I also have some problems I'm going to post on Blackboard for this. The green part was confusing. You mean the big part in the middle, right? The algebra part? Yeah. So we'll do some more of those. But just remember, if you go back and look through this later, once you finally piece this together, you'll see it all is just algebra. The only thing that's new is the summations. It's navigating through those, because that's something you're not used to. Once you get used to those, this is just a bunch of algebra. But yeah, you need a little practice, and we'll do some more examples tomorrow. And I started to say I will post some problems on Blackboard that I want you to do for this in this style. And so I'll put those up tomorrow, let you catch up on everything else, and then we'll do more of this tomorrow and get you going on 4.5. And then 4.6 and 4.7 will go pretty quickly. So I think we'll probably spend most of tomorrow doing some more of these. Sound good? When's the next test? Sometime later next week. Let's see how we do by like this Thursday. It'll cover chapter 4. And so once we get through 4.5, 4.6 goes very quickly. 4.7 slows down a little bit, but once we get over the hump in that section, the rest of the chapter is just downhill as far as there's not a lot of development needed. You can jump right into doing problems. So I would think no later than later next week. Let's say Friday at the latest, we should be good to go. I'd say if you're good with antiderivatives so far, the only other big thing to get a hold of is this stuff that we're doing right here in this example. And the stuff after this I don't think has as steep a learning curve. By the way, I will put up your tests here later today or by tomorrow. They're all graded. I just need to figure out the ratio I want for the first part and the second part. And then once I've got that figured out, I'll load them into your folders. Next exam covers all of chapter 4. Oh, you mean the one after? You mean exam 4, Ethan? You mean the next one? Okay. Yeah, the last one will be chapter 5, as much of it as we can get done. And there's a little bit in the last half of that chapter. If we don't quite get it all done, it's not that big a deal. As long as we get the first half done, we're good. Not more complex integration, applications of integration. That is, what are we using integration for right now? To find area under curves, essentially. Integration is used for a lot more than just that. So in chapter 5 we try to do some other things with integration. Disk and washer method is in the last test in chapter 5. So of all the things we definitely want to talk about in chapter 5 for sure, we definitely want to get to that stuff, and that's in the first part of the chapter. So for you guys that have done this before, some of the stuff that we might not get to is the stuff on centers of mass, moments of mass, fluid pressure, force work. We probably won't get to all of that stuff. We'll try and do what we can, but if we have to leave off a little bit towards the end, it'll be okay. All good? You want some homework? I'll go ahead and put up your homework here. You might as well have it. Sure. 19, 25, 27, 29, 31, 33, 37, 51, 53. No, this is 4-5, this part. Depending on how far we get tomorrow, I'll give you some 4-6. 4-6 is a pretty easy section. This is the section where you're doing the limits of the Riemann sums, like this example we just did. Okay, now I will say the first part of this homework, I'm not sure how far, is basically just getting used to sums. Meaning you're not doing limits of Riemann sums for the whole homework. So for example, earlier in the homework he might ask you something like, what's the sum k equals 1 to 10 of k minus k squared? And so basically 1 through 25 odd, and this from 4, 5. 1 through 25 odd. You mean you're talking about from 4, 5, Ethan? Oh, I did. Okay. Yeah, that's right. That's why I have that written down. So that means this is kind of redundant here. I wasn't even paying attention to the fact that the first ones weren't there. So yeah, I guess it's what, 1 through 33 odd or something like that. Yeah, so I think when I say the first part is getting used to sums, I think that's largely this part right here. So you know, like, what is this one? We know the summation of the k's is n times n plus 1 over 2. We know the summation of the k squareds is n times n plus 1 times 2n plus 1 over 6. So he's just got you playing with these formulas. This would be k equals 1 to 10 k minus k equals 1 to 10 k squared. What's the sum k equals 1 to 10 of k? It's 10 times 11 over 2. That's by this formula. Minus, what's the sum of the k squareds? Well, it's n, right, which is still 10, times n plus 1, which is 11, times 2n plus 1, which is 21, over 6, and then that's just the thing you can compute. So, you know, part of what you guys were saying before about the difficulty in getting through those sums, I think that's what he's trying to address here with these first problems in that homework, just to get you used to manipulating sums and calculating sums. And so if you can work through these problems, that might help you get used to looking at these and using them. So then when we do a few more limits of Riemann sums tomorrow, this won't maybe slow you down as much, which I think that's the part right now that's hurting your eyes when you look at this stuff. And so here's your homework for 4 or 5, plus I'm going to put some Blackboard problems, you know, like I've done in the past, like 5 or 6 problems. I'll put those up, I guess tomorrow, because you've got plenty to do here with the book homework for now. Sound good? Yay! Thank you for that. You're very generous with your praise. Okay, I have another class to get to. See you guys in the morning. Don't any of you guys have mics this morning? Okay. Oh, is that what it is? Why do I have a mic? I'm not supposed to have a mic. Okay, I'm going. Now that one I can accept.